There's a monster hiding in the universe, a cosmic predator so massive it defies comprehension. And right now, we're going to discover exactly how big these things can get before the universe itself says, enough. Picture this, a black hole 40 billion times more massive than our Sun. Its event horizon stretches so far that light, traveling at 186,000 miles per second, would take days just to cross from one edge to the other. You could fit our entire solar system inside it, 60 times over. And here's the unsettling part. We've found several of these cosmic titans lurking in distant galaxies, but they can't grow forever. Somewhere, somehow, the universe has drawn a line in the sand. The question isn't whether black holes have a size limit. They do. What we're after is far more fascinating. Why does that limit exist at all? If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. You'd think the answer would be simple. After all, black holes are gravity incarnate. They pull in everything around them, growing larger with each meal. Why wouldn't they just keep eating forever, swelling to infinite proportions? The mathematics of Einstein's equations certainly allow for it. There's no theoretical ceiling written into general relativity that says, black holes must stop at X solar masses. And yet, when we scan the cosmos with our most powerful instruments, we notice something peculiar. The largest black holes we've ever discovered hover around the same upper boundary, somewhere between 40 and 70 billion solar masses. A few controversial measurements push higher, but even those don't breach 100 billion solar masses. That's suspicious. In a universe filled with trillions of galaxies, each potentially harboring a supermassive black hole at its core, why aren't we seeing cosmic leviathans 1,000 times larger? Why aren't there black holes weighing as much as entire galaxy clusters? The answer lies not in the black holes themselves, but in the way they feed. Imagine you're trying to drink from a fire hose. Sounds straightforward. Point it at your mouth and let physics do the work. Except the instant that pressurized water hits your face, you're knocked backward. The very thing you're trying to consume becomes a barrier to consumption. Black holes face a similar paradox, though the physics involved is considerably more violent. When matter spirals toward a black hole, it doesn't just fall straight in like water down a drain. Instead, it forms what astronomers call an accretion disk, a swirling maelstrom of superheated gas and dust that orbits the black hole at relativistic speeds. This disk gets hot, not campfire hot, not even surface of the sun hot. We're talking millions of degrees hot, so energetic that it radiates across the entire electromagnetic spectrum, from radio waves to X-rays. Here's where things get interesting. That radiation doesn't just vanish into space. It pushes outward with tremendous force, creating a pressure that acts against the very gravity trying to pull matter inward. At some point, for any given black hole, the outward push of radiation equals the inward pull of gravity. This balance point is called the Eddington Limit, and it represents the maximum rate at which a black hole can realistically feed. Now, you might be thinking, okay, but even if a black hole can only eat so fast given enough time, couldn't it still grow arbitrarily large? That's the natural assumption. Feed slowly but steadily for billions of years, and eventually you'd build up to truly stupendous masses. Except the universe has thrown several wrenches into this plan. First, there's the age problem. The universe is roughly 13.8 billion years old. That sounds like plenty of time for black holes to bulk up. Except when you do the math on accretion rates, even assuming continuous feeding at the Eddington limit, you run into an awkward conclusion. A black hole starting from stellar mass, say 20 or 30 times the mass of our Sun, simply cannot reach 60 billion solar masses in the time available. Not even close. This creates a puzzle that has haunted astrophysicists for decades. We observe quasars in the early universe, cosmic beacons powered by black holes that already weigh billions of solar masses when the universe was less than 1 billion years old. How did they get so massive so quickly? It's like finding a full-grown oak tree in a forest that's only been around for a week. The leading hypothesis involves what scientists call black hole seeds. The idea is that the first generation of black holes didn't start small. Instead of forming from collapsed stars weighing 20 or 30 solar masses, perhaps the early universe produced much larger starting points. Imagine a primordial cloud of hydrogen and helium, pristine and untouched by stellar fusion, collapsing directly into a black hole weighing hundreds of thousands of solar masses. Give that seed enough time and favorable conditions, and you could grow a supermassive black hole before the universe reaches its first billion years. But even this solution has limits. Recent research has revealed something unexpected about black hole growth. It turns out that as black holes approach truly enormous sizes, somewhere around 10 billion solar masses, the physics of their accretion disks fundamentally changes. The innermost stable circular orbit, the closest distance at which matter can orbit without immediately spiraling inward, moves farther and farther from the event horizon as the black hole grows. Eventually, this orbit moves so far out that the accretion disk itself becomes gravitationally unstable. What happens next is almost comical from a cosmic perspective. The disk, instead of feeding the black hole, starts forming stars. All that gas and dust that should be falling into the gravitational abyss instead coalesces into new stellar systems, orbiting safely outside the danger zone. The black hole essentially chokes on its own food supply. This self-limiting mechanism kicks in around 10 billion solar masses and becomes increasingly severe as black holes grow larger. By the time you reach 50 billion solar masses, the trickle of matter actually reaching the black hole has slowed to a crawl. The radiation from the inner disk puffs up, launching powerful jets and outflows that actively push material away. The black hole transitions from voracious feeder to cosmic gatekeeper, preventing its own growth. The theoretical calculations suggest an upper limit of roughly 50 billion solar masses for a non-spinning black hole, or up to 270 billion solar masses for a black hole rotating at maximum speed in the same direction as its accretion disk. That second number represents an absolute ceiling, the point at which the physics of accretion breaks down entirely, regardless of how much material surrounds the black hole. But wait, doesn't this conflict with some observations? You've probably heard of TON 618, often cited as one of the largest black holes ever discovered. Estimates place its mass somewhere between 40 and 66 billion solar masses, right up against our theoretical limit. Then there's Phoenix A, which some sources claim weighs in at a staggering 100 billion solar masses. If that measurement is accurate, it would blow our theoretical framework apart. Except there's a problem with Phoenix A. The mass estimate comes from indirect measurements, and when researchers dug into the actual published data, they found something surprising. The only peer-reviewed paper that included Phoenix A calculated its mass at 19 billion solar masses. Still enormous, but nowhere near the 100 billion figure floating around online. The confusion likely arose from someone misreading the data or conflating different measurements. It happens more often than you'd think in science communication. What about the cosmic horseshoe galaxy? Astronomers recently announced a black hole there weighing 36 billion solar masses, measured with unprecedented precision using gravitational lensing. That technique, watching how the black hole's gravity bends light from background galaxies, provides one of the most reliable mass estimates we have. And notably, it falls comfortably within our theoretical predictions. The pattern holds across dozens of supermassive black holes. The largest confirmed specimens cluster between 30 and 70 billion solar masses. A few push higher, but none definitively exceed 100 billion. This consistency across multiple independent observations suggests we're seeing a real physical boundary, not just a measurement artifact. So that's it, right? 50 billion solar masses for typical cases, maybe 270 billion for the absolute maximum under perfect conditions. Case closed. Not quite. Because there's a loophole in this limit, a way for black holes to potentially grow even larger, and it involves one of the most violent events in the entire cosmos. When two galaxies collide, and they do collide regularly throughout cosmic history, their central black holes eventually spiral toward each other. This death dance can last millions of years, but the conclusion is inevitable. The black holes merge, creating a single combined object whose mass is the sum of both progenitors, minus a small amount of energy radiated away as gravitational waves. These mergers completely bypass the accretion disk problem. No radiation pressure to fight against, no Eddington limit to respect. Just pure gravitational addition. If a 50 billion solar mass black hole merges with another 50 billion solar mass black hole, you get a 100 billion solar mass monster. Merge that with another giant, and you push even higher. This raises an intriguing possibility. Could there be black holes out there that grew past the accretion limit through mergers alone? Ultramassive behemoths lurking in the cores of galaxy clusters, fed not by gas and dust, but by cannibalism. The math suggests it's possible, but rare. Galaxy mergers happen frequently on cosmic timescales, but supermassive black hole mergers are trickier. The black holes need to lose enough orbital energy to actually come together, and that process slows dramatically once they get within a few light years of each other. This is called the final parsec problem, and it's one of the outstanding puzzles in astrophysics. Some theoretical models predict that in the far future, when galaxy superclusters collapse under their own gravity, we might see black holes reach truly stupendous masses, perhaps as high as 100 trillion solar masses. These hypothetical objects, dubbed stupendously large black holes, or SLABs, would dwarf anything we observe today. Their event horizons would span entire galactic volumes, but that's billions of years away, if it happens at all. Right now, in our current epoch of cosmic history, the evidence points to a clear practical limit. Black holes can reach 50 to 70 billion solar masses through normal growth, with a theoretical maximum of 270 billion under ideal conditions. Anything larger requires special circumstances, multiple mergers, unusual feeding patterns, or a universe much older than our own. And here's something to consider as we close this chapter of our investigation. Every limit we've discussed so far assumes the black hole is feeding on ordinary matter, gas, dust, stars. But what if there are other ways to feed a black hole? What if, in the extreme environments of the early universe, or in regions of space we haven't yet observed, different rules apply? That's where things start getting really interesting, because the universe has a habit of surprising us with edge cases and exceptions. And when it comes to the absolute largest black holes that could possibly exist, we need to look beyond accretion disks and merger rates. We need to examine the very fabric of space-time itself. The fabric of space-time isn't just a metaphor. It's a physical reality that bends, stretches, and warps under the influence of mass and energy. And when we're talking about the absolute limits of black hole size, we need to understand what happens when you push space-time to its breaking point. General relativity tells us that mass curves space-time. The more concentrated the mass, the steeper the curve. A black hole represents the ultimate extreme, mass compressed into such a small volume that space-time curves infinitely at the center. The event horizon marks the point of no return, where space-time is curved so severely that not even light can escape. Now here's where it gets fascinating. The size of that event horizon, the Schwarzschild radius, scales directly with mass. Double the mass, double the radius. This seems straightforward until you consider what it means for truly massive black holes. A stellar mass black hole, say 10 times the mass of our Sun, has an event horizon about 60 kilometers across, small enough to fit comfortably inside most cities. But scale up to 1 billion solar masses, and you're looking at an event horizon roughly the size of Uranus's orbit. At 66 billion solar masses, the estimated mass of Ton 618, the event horizon stretches 1,200 astronomical units across. That's 40 times the distance from the Sun to Pluto. Think about that for a moment. The boundary of this black hole is larger than our entire solar system. Light itself, traveling at 300,000 kilometers per second, would take nearly 2.5 weeks just to cross from one side to the other. But size alone doesn't capture the full strangeness. Because as black holes grow larger, something counterintuitive happens. They become less dense. You probably weren't expecting that. We think of black holes as infinitely dense points, and at the singularity, the mathematical center, that's true. But density is mass divided by volume, and for calculating average density, we use the volume inside the event horizon. As black holes grow, their volume increases faster than their mass. The relationship is cubic versus linear. Triple the radius and you've increased the volume by 27 times, but the mass by only 3. A stellar mass black hole has an average density roughly 100 billion times that of water, incomprehensibly dense. But a supermassive black hole with 1 billion solar masses, its average density is about that of air at sea level. Ton 618, at 66 billion solar masses, has an average density less than water. You could theoretically swim through its event horizon without immediately noticing anything wrong. The tidal forces at the horizon of such a massive black hole are actually quite gentle. This seems paradoxical until you remember that the event horizon isn't a physical surface. It's simply the boundary where escape velocity equals the speed of light. For smaller black holes, that boundary sits incredibly close to the crushing singularity at the center. For ultramassive black holes, there's a lot of relatively empty space between the horizon and the center. But there's a limit to how much you can stretch space-time. And that's where the really interesting physics comes in. Space-time isn't infinitely flexible. It has properties, structure, resistance. When you create extreme curvature, you're not just bending an abstract mathematical construct. You're warping the actual fabric of reality in ways that have physical consequences. At the quantum level, intense gravitational fields do strange things. They create particle pairs out of the vacuum itself. This is Hawking radiation, the process by which black holes slowly evaporate. Virtual particle pairs pop into existence near the event horizon, and occasionally one particle falls in while the other escapes, carrying away a tiny amount of the black hole's mass energy. For stellar mass black holes, this evaporation is absurdly slow. The black hole at the center of our galaxy would take something like 10 to the 67 years to evaporate, far longer than the current age of the universe. But the principle matters. It reveals that black holes aren't eternal, unchanging objects. They interact with the quantum vacuum in measurable ways. Now scale this up to ultramassive black holes. The Hawking radiation becomes even more negligible. These monsters would take unimaginably long to evaporate. But other quantum effects might come into play. We don't have a complete theory of quantum gravity yet, but most physicists suspect that at some scale, quantum mechanics and general relativity must intersect in ways that impose fundamental limits. Could there be a maximum curvature of space-time, a point beyond which you simply can't compress mass any further, not because of radiation pressure or disk dynamics, but because the laws of physics themselves say no? Some theories suggest this might happen at the Planck scale, the smallest meaningful length in physics, about 10 to the negative 35 meters. Below this scale, our current understanding of space-time breaks down. The quantum foam of virtual particles and fluctuating geometry becomes dominant. If there's a fundamental limit to black hole size, it might emerge from these quantum effects. But here's the problem. We're nowhere close to that limit, not even in the ballpark. The Planck density is 10 to the 93 grams per cubic centimeter. Even the smallest stellar black holes have average densities far below this. Ultramassive black holes don't even register on this scale. So quantum gravity effects, whatever they are, probably aren't setting the upper limit we observe, which brings us back to the astrophysical limits we discussed earlier. 50 billion solar masses for normal spin, 270 billion for maximal rotation. These aren't fundamental limits imposed by the laws of physics. They're practical limits imposed by how black holes interact with their environment. But what if we remove the environment entirely? What if we imagine a black hole floating in completely empty space, with nothing to accrete, no radiation to produce, no external forces acting on it? In this scenario, what's the maximum size? The answer is surprising. There isn't one. In pure general relativity, you can have a black hole of any mass whatsoever. 1 solar mass, 1 trillion solar masses, 1 Google solar masses. The math works regardless. The event horizon just keeps scaling up proportionally. There's no point where the equations say, stop, this is impossible. This seems to contradict everything we've discussed about growth limits. But remember, Those limits are about how black holes can grow, not how large they can theoretically be. It's the difference between asking, what's the tallest building we can construct, versus, what's the tallest structure that could theoretically exist without collapsing? The second question has a different answer. On Earth, we're limited by materials and engineering, but on a planet with lower gravity, or with stronger materials, or with different constraints, you could build much taller. The physics of structure doesn't impose an absolute height limit. It imposes limits based on specific conditions. Same with black holes. The 50 billion solar mass limit is based on growth through accretion in our current universe with its current density and composition. Change those conditions and the limit changes. In the early universe, conditions were very different. Higher density, more available gas, different radiation backgrounds. Some models suggest that black holes forming in the first billion years after the Big Bang could have grown much faster than modern accretion physics would allow. They might have had access to super-Eddington accretion rates sustained over long periods. Or they might have formed from the direct collapse of massive gas clouds, starting with much larger seed masses. This could explain some puzzling observations. Astronomers have found quasars, supermassive black holes actively feeding, less than 1 billion years after the Big Bang. Some of these black holes already have masses exceeding 1 billion suns. That's barely enough time for a stellar mass black hole to grow through normal accretion, even at maximum efficiency. The James Webb Space Telescope has made this problem worse, or more interesting, depending on your perspective. It's found even more massive black holes at even earlier times. Black holes that shouldn't exist according to our standard models. They're too big, too soon. This suggests either our models are wrong, or black holes in the early universe played by different rules. Maybe they had access to growth mechanisms we don't see today. Maybe the conditions in primordial galaxies allowed for sustained super-Eddington accretion. Maybe they formed through exotic processes we haven't considered. One intriguing possibility involves dark matter. We know dark matter exists. We can see its gravitational effects throughout the universe, but we don't know what it is. Most candidates are particles that barely interact with normal matter. They don't emit light, don't absorb light, don't collide with atoms. They just exert gravitational force. But what if some forms of dark matter could be captured by black holes? Not through the normal accretion disk process, but through direct capture. Dark matter particles passing near a black hole could lose energy through gravitational interactions and fall in without producing any radiation. This would be completely invisible growth. No luminosity, no feedback, no Eddington limit to worry about. The math is speculative, but if this process is efficient, it could allow black holes to grow much larger than accretion-based limits would allow. A black hole sitting in a dense halo of dark matter could balloon to enormous size over cosmic time without ever producing a photon. We have no direct evidence for this, but it's worth considering because dark matter outweighs normal matter by a factor of 5 in our universe. If even a fraction of that dark matter can be captured by black holes, it represents a massive reservoir of potential growth. Then there's the question of primordial black holes. These hypothetical objects would have formed in the first fraction of a second after the Big Bang, from quantum fluctuations in the density of space itself. Unlike black holes that form from collapsing stars or gas clouds, primordial black holes could have any mass. From microscopic to supermassive, all formed in that earliest instant. If primordial black holes exist, some could have started with enormous masses right from the beginning. No need to grow through accretion or mergers. They'd simply be born huge, and they'd have the entire age of the universe to accrete additional mass on top of their already massive starting point. Again, this is speculative. We've never definitively detected a primordial black hole. But if they exist, they could potentially exceed the normal growth limits by starting far ahead of the game. All of these exotic possibilities share a common thread. They suggest that the limits we observe today might not be fundamental limits. They might be contingent on current conditions, modern environments, the specific epoch of cosmic history we happen to inhabit, which raises a profound question. Are the largest black holes we observe today, TON 618, Phoenix A, the ultramassive giants lurking in galaxy cores, are these the largest black holes that have ever existed? Or are they just the largest that can exist now, under current conditions? The universe is 13.8 billion years old. That's a long time, but it's not infinite. Perhaps in the early universe, in those first chaotic billion years, even larger black holes formed through processes we no longer see. Monsters that dwarf TON 618. Behemoths that would make Phoenix A look modest. If they existed, where are they now? One possibility is that they're still out there, lurking in the cores of distant galaxies, too far away or too quiet for us to detect yet. Another possibility is that they merged with other black holes, their mass distributed among multiple descendants. Or perhaps they're surrounded by so much matter that we can't see them clearly, hidden behind veils of gas and dust that block our view. The universe is vast and old. We've surveyed only a tiny fraction of it. Every year we push our telescopes deeper, looking further back in time. And every year we find new surprises. Black holes where they shouldn't be. Galaxies that shouldn't exist. Structures that challenge our models. It would be premature to say we've found the absolute largest black hole that can exist. What we might be witnessing instead is the largest black holes that can exist right now, under the specific conditions of today's universe. That distinction matters more than you'd think. The universe has been through several distinct eras since the Big Bang. Each era had different physics, different densities, different temperatures. The early universe was hotter, denser, more chaotic. Gas clouds were pristine, pure hydrogen and helium, no heavy elements to complicate things. Star formation worked differently. Galaxy collisions were more frequent. The entire cosmic environment was alien compared to what we see today. In that early chaos, perhaps different rules applied to black hole growth. Perhaps the mechanisms that limit black holes today, the accretion disk instabilities, the radiation pressure, the angular momentum problems, perhaps those constraints were weaker or absent entirely. If so, the early universe might have been a breeding ground for black holes that dwarf anything we see now. There's some evidence pointing in this direction. The James Webb Space Telescope keeps finding supermassive black holes that shouldn't exist yet. Black holes with billions of solar masses less than a billion years after the Big Bang. According to standard growth models, these objects had nowhere near enough time to reach their observed sizes. They're like finding a full-grown oak tree in a field that was bare dirt yesterday. Something doesn't add up. One possibility is that these early black holes started big, not from collapsing stars. Those only produce black holes up to maybe 100 solar masses, but from something else entirely. Direct collapse black holes formed when enormous clouds of gas collapsed all at once without fragmenting into stars first. These could have masses of tens or hundreds of thousands of suns right from birth. Start with 100,000 solar mass seed in the dense early universe. Give it nearly 14 billion years to grow, and you might end up with something truly colossal, far larger than the theoretical limits we calculate for black holes forming today. But here's the catch. We've never directly observed a direct collapse black hole forming. We've found the ancient monsters that might be their descendants, but we haven't caught the formation process itself. Another pathway involves supermassive stars. Not normal stars, but behemoths that could only exist in the early universe's pristine gas clouds. Stars weighing hundreds of thousands or even millions of solar masses. These objects would be fundamentally unstable. Their cores would generate so much radiation that they'd constantly be on the verge of exploding. But if they could hold together long enough, they'd collapse directly into massive black holes without going through a supernova phase. No explosion means no mass loss. The entire star becomes the black hole. Computer simulations show these supermassive stars could form under the right conditions. Intense radiation fields that prevent normal star formation. Rapid inflows of cold gas that don't give the cloud time to fragment. It's a narrow window of conditions, but the early universe might have hit that window repeatedly in its first few 100 million years. The real question is what happened to these massive seeds afterward. Did they grow into the ultramassive giants we see today? Did they merge with each other, creating even larger monsters? Or did something else happen, something we haven't thought of yet? Recent observations are making this puzzle more complicated, not simpler. The more we look at the early universe with advanced telescopes, the more we find black holes that challenge our models. Not just their masses, but their properties. Some of these early quasars are too bright, too active, growing too fast. It's as if the early universe was somehow more efficient at building supermassive black holes than the modern universe is. Which brings us back to limits. The 50 billion solar mass ceiling we calculated, that's based on physics as we understand it today. The accretion disk dynamics, the radiation pressure, the angular momentum transport. All of that depends on conditions in the modern universe. But what if those conditions were different 13 billion years ago? What if the early universe allowed black holes to grow in ways that are no longer possible? Think about the Eddington Limit. That's the balance point where radiation pressure from infalling matter exactly matches the gravitational pull trying to drag more matter in. It sets a maximum rate at which black holes can grow through accretion. Except we keep finding black holes that appear to be violating this limit, growing faster than they should be able to, gaining mass at rates that shouldn't be physically possible. One explanation is super-Eddington accretion. Under certain conditions, thick accretion disks, strong magnetic fields, specific geometries, black holes might be able to accrete matter faster than the standard limit allows. The radiation doesn't escape as efficiently as it should. It gets trapped in the inflowing gas, carried down into the black hole rather than pushing outward. This could boost growth rates by factors of 10 or even 100. Super-Eddington accretion might have been common in the early universe. The gas was denser, the magnetic fields were stronger, the conditions were just right for this accelerated growth mode. If that's true, then early black holes could have reached masses in hundreds of billions or even trillions of solar masses before standard accretion physics kicked in and slowed them down. But there's a problem with this scenario. Where are they now? If the early universe was churning out black holes with hundreds of billions or trillions of solar masses, we should be finding them everywhere. Yet the largest black holes we observe top out around 100 billion solar masses, and even those are rare. Most ultramassive black holes sit in the 10 to 50 billion solar mass range. Maybe we're not seeing them because they're too far away. Light from the most distant regions of the observable universe is just now reaching us. Every year, our telescopes push a bit deeper, looking at earlier cosmic epochs. Perhaps the truly massive black holes are still out there, beyond our current detection limits, waiting to be discovered. Or maybe they merged. 200 billion solar mass black holes colliding would produce a 400 billion solar mass monster. Do that a few times and you could theoretically build something approaching 1 trillion solar masses. But black hole mergers don't happen in isolation. They require galaxies to collide first. And while galaxy mergers were more common in the early universe, they're still relatively rare events on cosmic timescales. Here's another wrinkle. Black hole spin. A black hole's spin affects how it grows. The event horizon of a spinning black hole is smaller than a non-spinning one with the same mass. This means a spinning black hole can pack more mass into a smaller region before running into accretion disk problems. The theoretical maximum mass jumps from 50 billion solar masses for a non-spinning black hole to 270 billion solar masses for a maximally spinning one. But there's a catch. Getting a black hole to spin at maximum speed is incredibly difficult. Every time it accretes matter, that matter carries angular momentum. If the angular momentum isn't aligned with the black hole's spin, it actually slows the black hole down. Only if the black hole consistently accretes matter from the same direction, all orbiting the same way, can it build up to maximum spin. That requires very specific circumstances that probably aren't common. None of the ultramassive black holes we've studied are spinning anywhere close to the maximum rate. Most are spinning at moderate speeds, suggesting their growth was chaotic. Matter falling in from many directions, cancelling out the angular momentum rather than building it up. This implies they're probably constrained by the lower mass limit, not the upper one. So we're left with a tension. Theory says black holes can't grow much beyond 50 billion solar masses under normal conditions. Observations show us black holes approaching, or possibly exceeding that limit. And we keep finding young black holes that grew too fast, too early, suggesting something we don't understand about the growth process. The answer might lie in a combination of factors. Maybe early black holes did start with massive seeds from direct collapse or supermassive stars. Maybe they went through brief periods of super-Eddington accretion during their most active phases. Maybe they merged with each other during galaxy collisions, temporarily pushing past the normal limits. And maybe, after reaching some critical mass, they settled into a more sedate growth pattern that we observe today. If that's the case, then the limits we calculate aren't absolute boundaries. They're more like speed limits that can occasionally be exceeded under the right circumstances. Most of the time, physics enforces these limits strictly, but during rare events, galaxy mergers, gas-rich collisions, direct collapse formation, the rules get bent. And in those exceptional moments, black holes can grow larger than standard theory predicts. This would explain why ultramassive black holes are so rare. They're not the norm, they're exceptions. products of unusual circumstances that only occur occasionally in cosmic history. Most black holes hit the 50 billion solar mass wall and stop growing, but a few, through luck or special conditions, push past that barrier and become the giants we observe at the edge of what's possible. Now, let's talk about the actual monsters we've detected. The current heavyweight champions. TON 618 sits roughly 10 billion light-years away, a quasar so bright it outshines everything around it. The black hole at its center weighs between 40 and 66 billion solar masses, depending on which measurement you trust. That's the equivalent of 66 billion stars like our Sun, compressed into a region about 800 times the distance from Earth to the Sun. Think about that. 800 astronomical units sounds like a lot until you realize the entire observable universe spans 93 billion light-years. This cosmic titan could fit comfortably inside our solar system, yet it contains more mass than entire galaxies. TON 618's Schwarzschild radius, the boundary of its event horizon, stretches roughly 120 billion kilometers. Light traveling at 300,000 kilometers per second would take about 2.5 days just to cross from one side to the other. Not to escape, mind you, just to traverse the diameter of the point of no return. But TON 618 might not even be the champion. Phoenix A lurks in a galaxy cluster 8.5 billion light-years away. Some measurements put its mass at 100 billion solar masses. Others suggest 19 billion. The discrepancy isn't a typo or a mistake. It reflects how insanely difficult it is to weigh something that massive at that distance. Here's the problem. We can't just point a telescope at a black hole and read its mass. Black holes don't emit light, they absorb it. So we measure them indirectly by watching how they affect their surroundings. Gas swirling around them, stars whipping past at ridiculous speeds, gravitational lensing bending light from background galaxies. Each method has uncertainties. Gas motion depends on the accretion disk structure, which we model but don't fully understand. Stellar velocities require knowing exactly how far away the stars are, which introduces error. Gravitational lensing depends on the mass distribution of everything between us and the lensed object, not just the black hole. Stack those uncertainties together and you get measurement ranges that span tens of billions of solar masses. Phoenix A could be twice as massive as TON 618, or half its size. We genuinely don't know yet. The Able 1201 black hole offers slightly better certainty. It weighs about 30 billion solar masses, making it smaller than the others, but still absurdly massive. What makes Able 1201 interesting is how we measured it, through gravitational lensing so precise that researchers feel confident about their number. This black hole bends light from a background galaxy into a nearly perfect Einstein ring. By analyzing exactly how that light curves, scientists reconstructed the mass distribution with unusual accuracy. They're not guessing based on gas motion or stellar orbits. They're reading the space-time curvature directly. That 30 billion solar mass measurement sits right near the theoretical limit for non-spinning black holes. It's exactly where physics predicts growth should stall out, which makes it a crucial data point for understanding whether our theories work. Then there's the black hole in the cosmic horseshoe galaxy, recently measured at 36 billion solar masses. Located 5 billion light-years away, it whips nearby stars around at speeds that should be impossible unless something extraordinarily massive sits at the center. The gravitational lensing it creates forms a beautiful arc of distorted light, giving the galaxy its horseshoe nickname. What's striking about these ultramassive black holes isn't just their size, it's their distribution. They're rare, incredibly rare. Most galaxies contain black holes ranging from millions to billions of solar masses. The Milky Way's black hole, Sagittarius A star, weighs about 4 million solar masses. That's respectable, but it's a lightweight compared to the monsters we've been discussing. Andromeda's central black hole comes in around 100 million solar masses, still nowhere close to the ultramassive category. You have to search through thousands of galaxies to find one with a black hole exceeding 10 billion solar masses. And the ones pushing past 50 billion, those are 1 in a million finds. This rarity tells us something important. These giants aren't the natural endpoint of black hole evolution. They're outliers, exceptions created by special circumstances that don't occur often in cosmic history. But here's what keeps astronomers up at night. We keep finding them in the early universe. J0313-1806 exists as it was just 670 million years after the Big Bang. It contains a black hole weighing 1.6 billion solar masses. That might sound small compared to TON 618, but remember, the universe was barely 500 million years old when this black hole formed. Standard accretion theory says this shouldn't exist. There simply wasn't enough time for a stellar mass black hole seed to grow that large, even if it fed continuously at the Eddington limit the entire time. ULAS J 134 2 plus 0 928 formed even earlier, just 690 million years after the Big Bang. Its central black hole weighs 800 million solar masses. Again, impossible according to conventional growth models. The James Webb Space Telescope keeps making this problem worse. Every deep field observation reveals more supermassive black holes existing at times when they shouldn't. Black holes exceeding 1 million solar masses at redshifts beyond Z equals 8, when the universe was less than 5% its current age. These discoveries force one of three conclusions. Either black holes grew much faster than we think possible through some mechanism we don't understand, or they started with much more massive seeds than stellar collapse can produce, or our timeline for cosmic history is somehow wrong. That last option seems unlikely. Multiple independent methods confirm the universe's age at 13.8 billion years. So we're left wrestling with the first two possibilities. Maybe super-Eddington accretion was common in the early universe. The first galaxies were gas-rich, turbulent environments unlike anything we see today. Perhaps black holes could temporarily exceed the Eddington limit by orders of magnitude, gorging themselves on material before radiation pressure kicked in. Or maybe direct collapse black holes seeded the early universe with black holes weighing hundreds of thousands of solar masses right from the start. Skip the stellar phase entirely and collapse primordial gas clouds straight into massive black holes. Both scenarios require conditions we can't easily test. The early universe was a fundamentally different place. No heavy elements existed yet. Gas was pure hydrogen and helium. Star formation worked differently. Galaxy formation worked differently. Maybe black hole formation worked differently too. Computer simulations offer some support for direct collapse. Under specific conditions, pristine gas clouds, intense ultraviolet radiation preventing cooling, rapid infall, Models show black holes forming with masses around 30 to 40,000 solar masses. That's not quite enough to solve the problem by itself, but it helps. A 40,000 solar mass seed growing at the Eddington Limit for 700 million years could reach 1 billion solar masses. Barely. If everything went perfectly. The truth probably involves multiple factors working together. Some black holes started bigger, some grew faster, some merged with others during galaxy collisions. Stack those mechanisms and you might explain the observations. But every explanation requires pushing our theories to their limits or beyond. We're not dealing with well-understood physics operating in familiar regimes. We're extrapolating into extreme conditions where our models might simply be wrong. Take Phoenix A again. If its 100 billion solar mass measurement holds up, that black hole exceeds the theoretical maximum for a non-spinning black hole by a factor of 2, which means either it's spinning at near maximum velocity, unlikely given how difficult that is, or our theoretical maximum is wrong. Maybe the accretion disk physics we use to calculate the limit doesn't apply at these scales. Maybe there's some other growth mechanism we haven't considered. Maybe black holes this massive formed through a series of mergers rather than continuous accretion. The merger explanation is appealing because it sidesteps the accretion disk problem entirely. When two black holes merge, they combine their masses instantly. No accretion disk required, no Eddington limit to worry about. Just add them together. Galaxy mergers were common in the early universe. If each galaxy contained a moderately massive black hole, repeated mergers could build up ultramassive black holes without ever requiring super-Eddington accretion or massive seeds. But this creates its own problem. Black hole mergers release enormous amounts of energy as gravitational waves. Those gravitational waves carry away momentum, potentially ejecting the merged black hole from its galaxy entirely. Scientists call these recoil kicks. When two black holes merge, if their spins and orbits aren't perfectly aligned, the gravitational wave emission isn't symmetric. The asymmetry creates a net force that can kick the merged black hole sideways at speeds exceeding 1,000 kilometers per second. That's fast enough to escape most galaxies. So repeated mergers might not build up ultramassive black holes. They might scatter them into intergalactic space instead. Unless the mergers happen to be perfectly aligned, which seems statistically unlikely, or unless something we don't understand about the merger process prevents large recoil kicks, or unless ultramassive black holes are massive enough that even 1,000 kilometer per second kick doesn't give them escape velocity. Every answer raises new questions, which is frustrating if you want neat solutions, but exciting if you like unsolved mysteries. The physical scale of these objects defies intuition. TON 618's event horizon spans distances we usually reserve for describing planetary systems. You could fit our entire solar system inside it multiple times over. Every planet, every comet, every speck of dust orbiting the Sun would fall within the boundary of no return. Yet, from a galactic perspective, even TON 618 is tiny. Galaxies span hundreds of thousands of light years. Black holes span hundreds of astronomical units. That's a factor of millions in size difference. It's like comparing a grain of sand to a football field. The black hole, despite containing more mass than billions of stars, occupies almost no volume compared to its host galaxy. This creates an interesting measurement challenge. How do you accurately weigh something that small from millions or billions of light years away? It's like trying to measure the weight of a grain of sand on a beach in another country using only a telescope. Astronomers rely on the black hole's gravitational influence on its surroundings, but that influence weakens with distance. Stars orbiting far from the black hole barely feel its pull. Only objects very close, within a few light years, experience strong enough gravity to reveal the central mass. Measuring those close-in orbits requires extraordinary precision. You're tracking objects moving at thousands of kilometers per second across angular distances smaller than a pixel in most telescopes. Any error in distance, velocity, or position translates directly into uncertainty about the black hole's mass. This is why Phoenix A's mass estimate varies by a factor of 5, depending on the study. Different research teams using different methods get different answers. They're all looking at the same object, but the measurements are so difficult that systematic errors dominate. The situation should improve as telescopes get better. The James Webb Space Telescope can resolve structures at unprecedented distances. Future gravitational wave detectors might catch the mergers of these ultramassive black holes directly, weighing them through their gravitational wave signatures. Until then, we're stuck with uncertain measurements and competing theories. We know ultramassive black holes exist near the edge of what physics allows. We know they formed surprisingly early in cosmic history. We know they're rare, but not impossibly so. What we don't know is exactly how they grew so large, whether they can grow larger still, or what happens when they finally stop growing. The waiting game isn't optional. Black holes don't grow on convenient timescales. When TON 618 adds mass to itself today, that material spent billions of years falling inward. Matter doesn't drop straight into black holes like coins into a slot. It spirals, slowly, fighting against its own angular momentum the entire way. Angular momentum is why accretion disks exist at all. Imagine trying to throw a ball directly at a spinning merry-go-round. Unless your aim is perfect, the ball will miss and start orbiting instead. That's essentially what happens when gas clouds encounter a supermassive black hole. The gas has sideways motion relative to the black hole. That sideways motion prevents a direct fall. Instead, the gas settles into a disk. Think of water draining from a bathtub. The vortex forms because the water has angular momentum it needs to shed before it can exit. Black holes face the same problem at vastly larger scales. Within the accretion disk, friction does the heavy lifting. Material orbiting closer to the black hole moves faster than material farther out. This differential rotation creates friction between adjacent layers of gas. Friction generates heat, a lot of heat, enough to make the inner disk glow brighter than entire galaxies. But friction does something else too. It transfers angular momentum outward through the disk. Inner material loses angular momentum and spirals inward. Outer material gains angular momentum and moves outward. This process takes time, lots of time. For a supermassive black hole, material in the outer disk might take millions of years to work its way inward. The journey from the disk's edge to the event horizon isn't a quick trip. It's a slow spiral governed by the physics of viscous friction in magnetized plasma. This creates a bottleneck. The accretion disk can only funnel material inward as fast as friction allows. Push too much material into the disk too quickly and problems emerge. At low accretion rates, everything works smoothly. Material spirals inward, heats up, radiates energy, and eventually crosses the event horizon. The black hole grows steadily. The surrounding quasar shines bright but stable. Crank up the accretion rate and things get messy. When you try to feed a supermassive black hole too much material too fast, the disk becomes unstable. The inner regions heat up so much that radiation pressure starts pushing material away. This is called the Eddington Limit. Named after Arthur Eddington, this limit describes the maximum luminosity a black hole can sustain through accretion. Beyond that luminosity, radiation pressure equals gravitational pull. Material stops falling inward and gets blown away instead. Here's the catch. The Eddington limit depends on mass. More massive black holes have higher Eddington limits. They can accrete more material per year while staying below the threshold where radiation blows everything away. But ultramassive black holes face a different problem. Their size itself becomes an obstacle. Remember the innermost stable circular orbit? That's the closest distance where material can orbit a black hole without falling straight in. For non-rotating black holes, it sits at 3 times the Schwarzschild radius. For rotating black holes, it can be closer. The ISCO matters because it defines where the accretion disk ends. Material inside the ISCO doesn't orbit stably. It plunges inward on timescales too short for friction to matter. The region inside the ISCO is effectively the point of no return for orbiting material. As black holes grow more massive, their ISCO moves outward in absolute distance, not relative to the black hole's size, but in actual kilometers. For a billion solar mass black hole, the ISCO sits roughly 20 billion kilometers from the center. For a 100 billion solar mass black hole, it's 2 trillion kilometers out. That expanding ISCO creates problems for disk formation. Accretion disks are gravitationally bound structures. They hold together because their self-gravity exceeds the tidal forces trying to tear them apart. But there's a characteristic radius, called the self-gravity radius, where these forces balance. When a black hole grows massive enough, its ISCO can exceed its self-gravity radius. Material trying to form an accretion disk at the ISCO finds itself too far out. Tidal forces from the black hole overcome the disk's self-gravity. Instead of forming a stable disk, the material breaks up into smaller clumps. Those clumps don't feed the black hole efficiently. Many of them form stars instead. You end up with a ring of star formation orbiting the black hole, rather than a smooth accretion flow. The black hole's growth rate plummets. Research suggests this transition happens somewhere between 10 and 50 billion solar masses. Exactly where depends on the black hole's spin, the properties of the inflowing gas, and details of the disk physics we still don't fully understand. But the pattern holds across multiple studies. Once you cross that threshold, growing the black hole becomes extremely difficult. Not impossible, mergers can still add mass, but regular gas accretion stalls out. This might explain why we don't observe any confirmed black holes above 100 billion solar masses, not because they can't exist, but because they can't form through normal accretion in the age of the universe we've had so far. There's another complication, one that applies even before black holes reach the ISCO limit. When accretion rates get high enough, the physics of the accretion disk itself changes. Instead of a thin, flat disk, you get a thick, puffy structure. The disk inflates. Material doesn't spiral inward smoothly. It gets caught in turbulent eddies. Some of it gets blown out in powerful winds and jets. This puffed up state is called an advection-dominated accretion flow. It's inefficient. Most of the gravitational energy gets carried into the black hole with the infalling material rather than being radiated away. The black hole grows, but slowly, much more slowly than standard thin disk models predict. The transition to this inefficient accretion mode happens around 1 to 6 times 10 billion solar masses, right in the range where we stop seeing larger black holes. That's probably not a coincidence. You might wonder whether black hole spin helps. After all, a maximally spinning black hole has a smaller ISCO than a non-spinning one. Shouldn't that allow faster accretion? In principle, yes. A black hole spinning at its maximum rate could theoretically grow to 270 billion solar masses before hitting the ISCO limit. That's 5 times larger than the limit for non-spinning holes. But there's a problem. Getting a black hole to spin that fast is hard. Every time the black hole accretes material, the material carries angular momentum. If that angular momentum aligns with the black hole's spin, it spins up. If it's misaligned, it spins down. In realistic astrophysical environments, accretion happens from all directions. Gas clouds fall in from different angles. Galaxy mergers send material on chaotic orbits. The black hole's spin gets randomized. Computer simulations suggest that most supermassive black holes spin at moderate rates, not extreme ones. They're not stationary, but they're not near the maximum either, which means the practical mass limit sits closer to 50 billion solar masses than 270 billion. None of the ultramassive black holes we've observed show signs of extreme spin. Their accretion disks and jets match what we'd expect from moderately spinning black holes. If something spun up an ultramassive black hole to near maximum rotation, we should see it. We don't. So the 50 billion solar mass limit seems robust for black holes growing through gas accretion in the current universe. But what about the far future? In several trillion years, the universe will look very different. Dark energy will have pushed distant galaxies beyond our cosmic horizon. But within gravitationally bound structures, galaxy clusters and superclusters, gravity still wins. Those structures will continue collapsing. Eventually, entire superclusters might merge. When that happens, all the supermassive black holes in all the galaxies in those superclusters will eventually find each other. They'll merge into single ultramassive black holes with masses potentially reaching 10 to the 14th solar masses. That's 100 trillion times the Sun's mass. Larger than the current limit by a factor of 1,000. These hypothetical objects are called stupendously large black holes, or SLABs. Whether they'll actually form depends on the exact strength of dark energy and the future evolution of cosmic structure. Current observations suggest dark energy's strength is constant. If that's correct, most galaxy clusters will remain isolated. Slabs probably won't form in significant numbers, but if dark energy weakens over time, or if it's not truly constant, the future could include black holes far larger than anything possible today. There's something almost poetic about that. The largest black holes in the universe today might be dwarfed by the monsters that form in the distant future. Assuming the universe lasts that long, assuming dark energy behaves the way we think, assuming our understanding of gravity holds at those scales. Every assumption carries uncertainty, which brings us back to measurement. How confident should we be in any of these numbers? The theoretical limits rest on well-tested physics, general relativity, accretion disk theory, radiative transfer. But applying those theories to the most extreme objects in the universe always involves extrapolation. We've tested general relativity extensively in our solar system. We've confirmed it using binary pulsars and gravitational waves. But testing it around 100 billion solar mass black hole is different. The space-time curvature is more extreme. Quantum effects might matter in ways we haven't accounted for. Similarly, accretion disk theory works well for stellar mass black holes and moderate mass supermassive black holes. We can compare predictions to observations and they match. But extrapolating to ultramassive black holes means assuming the physics scales up without new phenomena emerging. Maybe it does. Maybe the 50 billion solar mass limit is solid. Or maybe there's something we're missing that allows larger black holes to form under special circumstances we haven't considered. The uncertainty in observational measurements compounds the theoretical uncertainty. When mass estimates for the same object vary by factors of 5, drawing firm conclusions becomes difficult. This is where future observations matter most. Better telescopes will nail down masses more precisely. Gravitational wave detectors sensitive to the mergers of supermassive black holes will provide independent mass measurements. Deep surveys will census more ultramassive black holes, telling us whether they're genuinely rare or just hard to find. Each new measurement either confirms or challenges the theoretical limits. If we discover a confidently measured black hole above 50 billion solar masses, something's wrong with the theory. If we survey millions of galaxies and never find anything above that limit, the theory looks stronger. Right now, we're in an intermediate state. The observations roughly match the theoretical predictions, but the error bars are large enough that surprises remain possible. So why does this matter beyond academic curiosity? Understanding the maximum size of black holes connects directly to understanding galaxy evolution. Black holes don't just sit passively at galactic centers. They shape their host galaxies through feedback processes. When supermassive black holes feed, they release enormous amounts of energy. That energy heats surrounding gas. It drives winds that can clear entire galactic regions of material. This feedback regulates star formation across the entire galaxy. The relationship between black hole mass and galaxy properties isn't coincidental. There's a tight correlation called the M-sigma relation. The mass of a galaxy's central black hole correlates precisely with the velocity dispersion of stars in the galaxy's bulge. Bigger black holes live in galaxies with faster moving stars. This correlation holds across multiple orders of magnitude. Why does this relationship exist? The leading explanation involves co-evolution. Black holes and galaxies grow together. When a galaxy forms through mergers, both the stellar population and the central black hole gain mass. The black hole's feedback energy regulates how much gas remains available for star formation. Too much black hole growth overheats the gas. Star formation shuts down. The galaxy stops growing. This creates a self-regulating system where black hole mass and galaxy mass stay proportional. If black holes couldn't grow beyond 50 billion solar masses, that sets an upper limit on the kinds of galaxies that can form. The most massive galaxies should host black holes near this limit, and that's exactly what we observe. The biggest elliptical galaxies contain the most massive black holes we've found. But there's something puzzling about the M-sigma relation. It's remarkably tight. The scatter is small. Black holes and galaxies track each other closely. This suggests the connection is fundamental. Yet black holes represent only about 0.1% of their galaxy's total mass. How does such a small component exert such precise control over something 10,000 times more massive? The answer involves leverage. Black holes might be small compared to galaxies, but when they're actively feeding, they're the most energetically dominant objects around. A quasar can outshine its entire host galaxy. That energy has to go somewhere. It couples to the surrounding gas through radiation pressure, winds, and jets. These mechanisms transfer energy from the black hole to the galactic scale. Think of it like a thermostat in a building. The thermostat itself is tiny compared to the building, but it controls the heating system that determines the building's temperature. Similarly, the black hole acts as a regulatory mechanism for the galaxy's gas supply and star formation rate. Now here's where the size limit becomes crucial. If there were no maximum black hole mass, the m-sigma relation should extend indefinitely. We should find black holes of arbitrary size in sufficiently massive galaxies. The fact that we don't, that there seems to be a ceiling around 50 to 100 billion solar masses, tells us something important about galaxy formation physics. The limit might arise from the same feedback processes that create the m-sigma relation. Once a black hole reaches a certain mass, its feedback becomes so powerful that it prevents further growth. The accretion disk physics changes. The inner regions of the disk puff up. Strong outflows and jets launch. These processes suppress feeding. This transition happens at a critical mass between 10 and 60 billion solar masses. Below that threshold, black holes can sustain stable accretion disks. Above it, the physics shifts into a different regime. The black hole effectively strangles its own food supply. But here's the interesting part. This self-limiting mechanism depends on how matter falls into the black hole. If gas spirals in at moderate rates through a geometrically thin disk, the limit applies. But there might be other feeding modes that bypass this restriction. Super-Eddington accretion represents one possibility. The Eddington limit defines the maximum luminosity a black hole can produce while maintaining spherical accretion. Above this limit, radiation pressure should blow away incoming material. But if the accretion isn't spherical, if it's clumpy or beamed, then material can fall in faster than the Eddington limit suggests. Early universe black holes might have grown through super-Eddington accretion. This could explain how billion solar mass black holes formed less than 1 billion years after the Big Bang. There simply wasn't enough time for them to grow at normal rates from stellar mass seeds. The James Webb Space Telescope has complicated this picture further. It's finding massive black holes at redshifts above 8. These objects existed when the universe was less than 700 million years old. Some show masses exceeding 1 billion suns. How did they grow so fast? Starting from a stellar mass seed of perhaps 100 solar masses requires continuous near-Eddington accretion for hundreds of millions of years. That's difficult to sustain. The black hole needs a constant supply of cold gas. The host galaxy needs to avoid disruptions that would cut off the fuel supply. One solution involves heavier seeds. Instead of starting with stellar mass black holes from the first generation of stars, maybe some black holes formed directly from collapsing gas clouds. These direct collapse black holes could start with masses around 10,000 to 100,000 suns. A heavier seed shortens the required growth time significantly. A 100,000 solar mass seed only needs to grow by a factor of 10,000 to reach 10 billion solar masses. A 100 solar mass seed needs to grow by a factor of 100 million. That's a dramatic difference. The conditions for direct collapse are stringent. You need a pristine gas cloud, pure hydrogen and helium with no heavier elements. Metals allow the gas to cool efficiently. Cool gas fragments into stars rather than collapsing into a single massive object. So direct collapse only works in the earliest cosmic epochs before stars contaminated the gas with heavy elements. You also need to prevent normal star formation. This requires a strong radiation field from nearby sources. The radiation keeps the gas warm enough that it can't fragment. Instead, it collapses as a single unit into a supermassive star. This star is unstable. It collapses into a black hole within a few million years. Computer simulations show this process can work, but it requires special circumstances. The conditions need to be just right. Most gas clouds don't satisfy the requirements. Direct collapse might produce only a small fraction of the black hole population. But that small fraction could seed the most massive black holes. Another possibility involves primordial black holes. These hypothetical objects formed in the first second after the Big Bang from density fluctuations in the early universe. If they exist, they'd have a huge head start. They could begin accreting immediately. By the time the first stars formed, primordial black holes might already weigh thousands of solar masses. The problem is, we haven't found clear evidence for primordial black holes. They remain theoretical. Some observations hint at their existence. Gravitational wave detections include black hole mergers with unexpected mass ratios. A few gravitational lensing events show anomalies consistent with compact objects in the right mass range, but nothing definitive. Whether through direct collapse, primordial origins, or super-Eddington accretion, the early universe clearly produced massive black holes faster than standard theory predicts. This challenges our understanding of both black hole growth and galaxy formation. The connection between black hole mass limits and galaxy evolution extends to cosmic structure formation. Galaxies don't exist in isolation. They're embedded in dark matter halos. These halos provide the gravitational potential wells that hold galaxies together. The most massive galaxies form at the centers of the most massive dark matter halos. These locations represent peaks in the cosmic density field. Matter flows toward them from surrounding regions. This creates the massive gas reservoirs needed to build big galaxies and feed supermassive black holes. But there's a limit to how massive dark matter halos can grow by a given cosmic time. The universe's expansion works against structure formation. As space expands, it becomes harder for gravity to pull material together. The largest structures forming today are smaller than the largest structures that formed in the past, relative to the universe's average density. This puts a time-dependent upper limit on galaxy masses, which means there's also a time-dependent upper limit on black hole masses. The most massive black holes today reflect the maximum halo masses available in the current epoch. Looking to the future, if dark energy remains constant, the universe will continue expanding forever. Structure formation will eventually cease. The largest dark matter halos will stop growing. The black holes they contain will have reached their maximum masses. Those maximum masses are set by the accretion physics we've discussed. 50 billion solar masses for typical conditions. maybe 270 billion if everything aligns perfectly. Those numbers represent the endpoint of black hole growth through normal feeding, but mergers can push beyond these limits. When two galaxies collide, their central black holes eventually merge. This adds their masses together without requiring accretion. A 50 billion solar mass black hole merging with another of equal size creates a 100 billion solar mass object. This bypasses the accretion limit. The merged black hole doesn't need to feed to reach that mass. It simply inherits the combined mass of its progenitors. If enough mergers occur, black holes could grow arbitrarily large. How often do galaxy mergers happen? That depends on environment and cosmic epoch. In dense galaxy clusters, mergers are more common. In the early universe, when galaxies were closer together, mergers happened more frequently. Today, in the relatively empty space between clusters, major mergers are rare. The Milky Way will merge with Andromeda in about 4 billion years. Their black holes will eventually combine. Sagittarius A star weighs about 4 million solar masses. Andromeda's black hole contains roughly 100 million solar masses. The merger will produce a black hole around 104 million solar masses. That's nowhere near the size limit, but it illustrates how mergers contribute to black hole growth. In denser environments with more galaxies, repeated mergers could build much larger objects. The role of mergers becomes especially important for the most massive black holes. Research suggests that for black holes above 10 billion solar masses, mergers contribute significantly to their growth history. These objects likely formed through a combination of accretion and multiple merger events. This creates an interesting evolutionary picture. Black holes start from seeds, stellar remnants, direct collapse objects, or possibly primordial black holes. They grow primarily through accretion during their host galaxy's active phase. Once they reach the critical mass where accretion becomes inefficient, merger events dominate further growth. The biggest black holes we observe today probably formed through this two-stage process. Early rapid accretion brought them to 10 or 20 billion solar masses. Subsequent mergers added additional mass. This explains both their enormous size and their relative rarity. Only the most massive galaxies in the richest environments have experienced enough mergers to build black holes at the upper mass limit. These galaxies sit at the centers of galaxy clusters. They've been accreting satellite galaxies for billions of years. Each captured galaxy contributes its central black hole to the growing monster at the cluster core. This is why the largest black holes live in the largest galaxies at the centers of the largest clusters. It's not coincidence. It's the natural outcome of hierarchical structure formation, combined with black hole merger dynamics. Looking beyond the present epoch, the future holds possibilities that stretch far beyond our current observational horizon. The universe we observe today represents merely one chapter in a story that extends trillions of years into the future. And in that distant future, black holes might grow to sizes that dwarf even the most massive objects we've discovered so far. Consider what happens in the extremely far future of the universe. Today, galaxies cluster together in groups and superclusters. These structures are bound by gravity but separated by expanding space. Dark energy drives the expansion, pushing unbound structures apart. But within gravitationally bound regions, dark energy's influence is negligible. Galaxy clusters remain intact. They continue evolving through internal dynamics. Over timescales of hundreds of billions of years, these clusters will evolve dramatically. galaxies within clusters will continue merging. Each merger adds mass to the central black hole. The process is slow but relentless. Eventually, entire clusters might collapse toward their centers. When this happens, all the black holes within that cluster will merge into a single object. How massive could such an object become? The calculations are staggering. A typical rich galaxy cluster might contain hundreds or thousands of galaxies. Each galaxy harbors a central black hole ranging from millions to billions of solar masses. If all these black holes eventually merge, the resulting object could reach truly stupendous proportions. Theoretical work suggests masses around 100 trillion solar masses are possible through this mechanism. That's 100,000 billion times the mass of our Sun. Such objects have been dubbed stupendously large black holes, or SLABs. They represent the ultimate endpoint of hierarchical structure formation carried to its extreme conclusion. These objects wouldn't form through accretion. Remember, accretion-based growth faces hard limits around 50 to 270 billion solar masses. Slabs would form entirely through mergers. As galaxy superclusters collapse over cosmic timescales, their constituent black holes would spiral inward and combine. No accretion disk would be involved. Just gravitational attraction and orbital decay leading to merger events. The timescales involved are almost incomprehensible. Current estimates suggest these processes would take place over 10 to 100 trillion years. That's thousands of times longer than the current age of the universe. We're talking about epochs so distant that all stars will have long since died. Galaxies will be dark graveyards of stellar remnants. The cosmic microwave background will have cooled to near absolute zero. In that cold, dark future, black holes will dominate. They'll be the primary repositories of mass and information. And through patient gravitational interactions spanning trillions of years, they'll continue growing through mergers long after accretion-based growth has ceased. What would such an object look like? The event horizon of a 100 trillion solar mass black hole would span roughly 10,000 astronomical units. That's about 40 times the distance to the Oort cloud. The entire solar system out to its farthest reaches would fit comfortably inside this black hole's event horizon, with room to spare. Light crossing this event horizon at 300,000 kilometers per second would take over 5 days to traverse the diameter. It's a scale that makes our own galaxy's central black hole look insignificant. Sagittarius A star, weighing 4 million solar masses, would be a mere speck compared to such a monster. But do these objects actually exist? That's the crucial question. The theoretical framework predicts their formation in the far future. But might some already exist in the present universe? Probably not. The conditions required for slab formation, complete supercluster collapse, haven't occurred yet. The universe isn't old enough. Even the oldest structures have only had 14 billion years to evolve. That's nowhere near sufficient time for supercluster scale collapse. However, some researchers have speculated that the largest black holes we currently observe might be early examples approaching this regime. Objects like Phoenix A, with disputed mass estimates ranging from 19 to 100 billion solar masses, push against the boundaries of what accretion alone can produce. If Phoenix A really does weigh 100 billion solar masses, that would place it firmly in the slab category. It would require explanation beyond standard accretion models. Multiple major mergers combined with near maximal accretion rates would be necessary. The environment would need to be extraordinarily rich in both gas and smaller black holes. The controversy surrounding Phoenix A's mass highlights a fundamental challenge in this field. Measuring black hole masses at cosmological distances is incredibly difficult. Most measurements rely on indirect methods. We observe the motion of gas or stars near the black hole. We use those velocities to infer the gravitational mass. But uncertainties accumulate quickly. For nearby black holes, we can use multiple independent methods to cross-check measurements. For distant quasars and ultramassive systems, we're often limited to a single technique: emission line widths, reverberation mapping, gravitational lensing. Each method carries systematic uncertainties that become larger at greater distances. This is why different studies of the same object can produce wildly different mass estimates. Phoenix A's range from 19 to 100 billion solar masses exemplifies this problem. Both numbers come from legitimate analysis using accepted techniques. They just employ different assumptions and data sets. TON 618 faces similar uncertainties. Earlier estimates placed it at 66 billion solar masses. More recent analysis using different emission lines suggests 40 billion solar masses. That's still enormous, still among the most massive known. But it's a 40% difference in estimated mass. These uncertainties matter tremendously when we're trying to understand the upper limits of black hole growth. Is 50 billion solar masses really the practical limit? Or can accretion-based growth reach 100 billion under optimal conditions? The observational data isn't yet precise enough to definitively answer these questions. What we can say with confidence is that the most massive black holes observed cluster around 10 to 40 billion solar masses. Very few confirmed measurements exceed 50 billion, and those that do carry significant uncertainties. This pattern supports the theoretical predictions about accretion-based growth limits. But the universe is large. We've only surveyed a tiny fraction of all galaxies. Perhaps rare objects exist that exceed even the most optimistic theoretical limits. Objects formed under special circumstances we haven't yet identified, or through mechanisms we haven't yet imagined. This brings us to an important philosophical point about scientific limits. When we calculate a theoretical maximum, we're making assumptions about physics and environment. Those assumptions might be wrong or incomplete. Nature often finds ways around apparent constraints. Consider the Eddington Limit. For decades, it was thought to represent a hard cap on accretion rates. Radiation pressure from the accreting material should balance gravitational infall at a specific luminosity. Exceeding that luminosity seemed impossible, yet we now know that super-Eddington accretion occurs regularly. Geometrical effects can collimate radiation into narrow jets. This reduces the radiation pressure in the equatorial plane where most accretion happens. The disk can be optically thick, trapping radiation before it can escape and push material away. Various mechanisms allow accretion to proceed faster than the classical Eddington limit predicts. The same might be true for the 50 billion solar mass limit on black hole growth. We've identified physical mechanisms that should prevent further growth beyond this point. The accretion disk becomes unstable. Star formation saps material before it reaches the black hole. The inner disk puffs up and launches powerful winds, but perhaps under special circumstances, these mechanisms don't operate as expected. Maybe extremely metal-poor gas behaves differently. Maybe particular spin configurations allow more efficient accretion. Maybe we're missing some crucial piece of physics that operates at these extreme masses. This is why observational astronomy remains so vital. Theory guides us. It predicts what should be possible. But nature always has the final word. If we discover a 200 billion solar mass black hole formed through accretion, we'll need to revise our theoretical understanding. The search continues. New telescopes probe deeper into the universe. The James Webb Space Telescope observes the earliest galaxies and quasars. Ground-based surveys catalogue millions of galaxies across cosmic time. Each observation adds to our statistical understanding of black hole populations. From this growing dataset, patterns emerge. The relationship between black hole mass and galaxy properties, the evolution of black hole populations over cosmic time, the frequency of the most massive objects. These patterns constrain theoretical models and point toward the true limits of black hole growth. What's becoming clear is that the universe has produced black holes spanning an incredible range of masses, from a few solar masses to perhaps 100 billion. That's a factor of 10 billion in mass. And each mass regime teaches us something different about the physics of gravity, accretion, and cosmic structure formation. The smallest black holes form from stellar collapse. They're governed by nuclear physics and supernova dynamics. Intermediate mass black holes remain mysterious. Their formation channels are still debated. Supermassive black holes grow through accretion and mergers in galactic centers. Their masses reflect their host galaxies' assembly histories and the hypothetical ultramassive black holes of the far future. They represent the ultimate endpoint of gravitational dynamics played out over cosmic timescales. They're the final period at the end of the sentence of structure formation, when all matter has collected into the deepest gravitational wells and all orbital energy has been radiated away through gravitational waves. We won't live to see these objects form. Neither will our sun or galaxy in their current forms. These are phenomena of the deep future, when the universe has aged by factors of thousands. But we can calculate their properties. We can predict their formation. We can imagine what the universe will look like when they dominate the cosmic landscape. In doing so, we're exercising one of humanity's most remarkable capabilities: the ability to understand processes occurring across timescales and distance scales that dwarf human experience. To calculate the behavior of objects we'll never directly observe. To peer into the far future through nothing but mathematics and physical law. That's the power of theoretical physics combined with observational astronomy. It lets us transcend our immediate circumstances and understand the universe in its full scope. From the smallest quantum fluctuations to the largest structures. From the first fraction of a second after the Big Bang to the cold heat death trillions of years hence. And through it all, black holes serve as markers, gravitational monuments recording the history of structure formation. Each one tells a story about where it came from, how it grew, and what limits it encountered. Together, they reveal the grand narrative of cosmic evolution. The story doesn't end with today's observations. It extends into futures we can calculate but never witness. Consider what happens when the current epoch ends. Star formation will eventually cease as gas supplies dwindle. Galaxies will complete their mergers, and black holes will enter a new phase of growth governed entirely by gravitational dynamics rather than accretion. In this distant future, black holes grow primarily through mergers. When galaxies collide, their central black holes spiral inward, losing orbital energy through gravitational wave emission. Eventually, they merge, creating a single more massive object. This process continues as galaxy clusters collapse under their own gravity. The mathematics of this progression is straightforward. Each merger adds mass. Larger black holes form from smaller ones. The process cascades upward in scale. Given enough time, superclusters themselves begin to collapse. Their constituent galaxies fall together. Their black holes merge into objects of truly stupendous mass. Theoretical calculations suggest these far future black holes could reach 10 to the 14th solar masses, 100 trillion times the Sun's mass. Objects so massive they dwarf anything we observe today by factors of thousands. These aren't violations of accretion limits. They form through an entirely different mechanism. No accretion disk, no radiation pressure, just pure gravitational merger over timescales of trillions of years. Will such objects actually form? That depends on the universe's ultimate fate. Current observations suggest the expansion will continue accelerating forever due to dark energy. In that scenario, most galaxy clusters become gravitationally isolated before they can collapse. The largest black holes may never form, but if dark energy behaves differently than we think, if the expansion eventually reverses or slows, then these stupendously large black holes become inevitable. They're the natural endpoint when gravity has infinite time to work. This represents a theoretical frontier. We're extrapolating physics across timescales that exceed the current age of the universe by factors of millions. Can we trust our equations that far into the future? Are there physical processes we haven't accounted for that might prevent such objects from forming? Nobody knows, but the mathematics is consistent. General relativity doesn't forbid these objects. There's no principle that prevents black holes from growing indefinitely through mergers. Let's return to today's universe and what we actually observe. The largest confirmed black holes cluster around 30 to 60 billion solar masses. TON 618 at 40 to 66 billion solar masses, depending on measurement technique. The black hole in Abell 1201 at 30 billion. The object in the cosmic horseshoe galaxy at 36 billion. These measurements come with uncertainties. Determining black hole mass from millions or billions of light years away isn't straightforward. We observe the motion of surrounding material. We measure Doppler shifts and orbital velocities. We apply gravitational physics to infer the central mass. Different techniques sometimes give different answers. TON 618's mass has been revised downward from earlier estimates. Phoenix A's mass remains controversial, with estimates ranging from 19 billion to 100 billion solar masses, depending on which study you trust. This uncertainty doesn't diminish the achievement. We're measuring objects billions of light years away, with masses so large they strain comprehension. Even the lower estimates place these black holes firmly in the ultramassive category. What's clear is that we've found black holes approaching theoretical limits. Whether it's 50 billion or 100 billion solar masses, we're observing objects near the maximum that accretion physics allows in the current epoch. That convergence between theory and observation is significant. It suggests we understand the fundamental physics. The limits we calculate aren't arbitrary. They reflect real physical processes operating in the universe. The accretion disk becomes unstable at high black hole masses. Gas doesn't flow smoothly inward. It fragments into stars before reaching the event horizon. The feeding process self-terminates. Growth halts not because the universe runs out of gas, but because the physics of accretion changes. This self-limiting mechanism explains why we don't observe 500 billion solar mass black holes formed through accretion. The universe has had time to create such objects if physics allowed. But physics doesn't cooperate. The accretion disk says no. Spin changes the calculation. A rapidly rotating black hole can grow larger before hitting the limit. The ergosphere allows matter to orbit closer to the event horizon. The innermost stable circular orbit moves inward. More efficient accretion becomes possible. But even with maximal rotation, the limit only increases to around 270 billion solar masses. That's the absolute maximum for accretion-driven growth under the most favorable conditions. And we don't observe black holes spinning fast enough to reach even that enhanced limit. Most supermassive black holes rotate at moderate rates. They've accreted material from random directions over billions of years. Sometimes the infalling gas adds angular momentum. Sometimes it subtracts. The net result is middling spin. Only a black hole fed by a perfectly aligned accretion flow maintains maximum rotation. That's geometrically unlikely over cosmic timescales. Random accretion washes out extreme spin states, so the practical limit sits closer to 50 billion solar masses. That's what physics delivers when you account for realistic accretion geometries and spin distributions. Now here's something fascinating about these limits. They depend on small-scale physics near the event horizon, the innermost stable orbit, the structure of the accretion flow, properties of the black hole's immediate environment. You might expect that objects with masses of tens of billions of suns would be governed by large-scale cosmological processes. The structure of the host galaxy, the distribution of dark matter, the history of galaxy mergers. But the maximum mass appears to be set by accretion disk physics, by what happens in the innermost few light years around the black hole. The tiny scale controls the large-scale outcome. This is physics at its most elegant. A simple principle operating locally cascades into a universal limit. Every supermassive black hole, regardless of when or where it formed, encounters the same barrier. Unless it grows through mergers, that pathway bypasses accretion entirely. Two black holes collide. Their event horizons merge. Mass adds directly. No accretion disk required. This is why the far future stupendously large black holes become possible. Mergers have no inherent mass limit. You can merge a 50 billion solar mass black hole with another 50 billion solar mass black hole. You get 100 billion solar masses. Merge that with another similar object. You get 200 billion solar masses. The process continues as long as black holes can find each other. In a collapsing supercluster, they will. Gravitational dynamics ensure it. The largest objects sink to the center of the collapsing system. They meet, they merge, mass concentrates. Given trillions of years, this produces objects whose event horizons span light years, whose gravitational influence extends across significant fractions of their host supercluster, whose tidal forces could shred entire solar systems at distances that seem safe for normal black holes. These objects exist purely in theoretical calculations. We'll never observe them. The universe isn't old enough yet. And by the time they form, if they form, humanity will be long extinct. Earth will have been consumed by the expanding sun. The Sun itself will be a cold white dwarf, then a black dwarf. But the mathematics predicts them, and mathematics has proven reliable when applied to black holes. We predicted stellar mass black holes before observing them. We predicted supermassive black holes before finding them. We predicted gravitational waves decades before detection. So when calculations point to stupendously large black holes in the far future, we take them seriously. Not as certainties, but as logical consequences of known physics extrapolated forward. This is how science probes beyond direct observation. We establish principles through experiment and observation. We express those principles mathematically. We follow the math wherever it leads. Sometimes it leads to predictions we can test. Sometimes it leads to predictions we can only contemplate. Black hole maximum masses fall into both categories. We can test whether today's black holes respect accretion-based limits. They do. We can contemplate what happens if mergers continue for trillions of years. The math suggests stupendous masses. Between these extremes lies our current understanding. Accretion builds black holes to around 50 billion solar masses in today's universe. Mergers can push them larger, though this requires special circumstances. The far future may host objects 1 million times more massive if cosmological evolution allows. These aren't just numbers. Each mass scale represents different physics, different formation mechanisms, different observable signatures, different implications for the structure of space-time. A 50 billion solar mass black hole curves space-time enough to create dramatic gravitational lensing. Its tidal forces could disrupt a star at distances of billions of kilometers. Its Schwarzschild radius exceeds the size of our solar system. A 10 trillion solar mass black hole represents something qualitatively different. Its event horizon spans light years. Stars orbit it at relativistic velocities at distances where they'd be safe around smaller black holes. The space-time curvature approaches levels where quantum effects might become relevant. We're still mapping this territory. Each new observation refines our understanding. Each theoretical advance clarifies what's possible. The conversation between theory and observation continues. What we've learned so far is that black holes have maximum masses determined by the physics of growth rather than fundamental limits. Accretion can build them to tens of billions of solar masses. Mergers can push them higher. The ultimate limits remain uncertain because they depend on cosmic evolution over timescales we can only calculate. The universe writes its own story. Black holes serve as punctuation marks, gravitational monuments to structure formation. Their masses encode information about cosmic history. The smallest record stellar collapse. The largest record billions of years of accretion and mergers, and somewhere in the distribution of masses lies a boundary. The point where accretion physics says no more. That boundary appears to sit around 50 billion solar masses for typical conditions, maybe 270 billion for perfect conditions. Above that limit, only mergers can build larger objects. Whether the universe will produce them depends on its ultimate fate. A question that connects black hole physics to cosmology, to dark energy, to the geometry of space-time itself. That's where the story reaches its natural conclusion, not with a definitive answer, but with a framework for understanding. Black holes can grow as large as physics allows, and physics sets different limits depending on how they grow. Today, we observe objects near the accretion limit. Tomorrow, in a future we can only calculate, mergers might produce something far larger. The universe, it turns out, isn't in the business of infinite anything. Not infinite speed, not infinite density, not infinite energy, and certainly not infinite black holes. What we've discovered through decades of observation and calculation is that reality imposes practical boundaries even on the most extreme objects imaginable. Black holes can grow enormous, tens of billions of times the mass of our Sun, but they can't grow forever. At least not through the mechanisms available today. The 50 billion solar mass ceiling for typical black holes isn't arbitrary. It emerges from the fundamental physics of how matter behaves near event horizons. The accretion disk becomes unstable. Gas fragments into stars instead of feeding the black hole. The inner regions puff up and launch powerful winds. The universe essentially says that's far enough through pure physical law. But here's what makes this genuinely fascinating. That limit isn't absolute. It's contingent on method. Grow through accretion and you hit the wall. Grow through mergers and the wall moves. Different physics, different constraints, different outcomes. This distinction matters because it reveals something profound about how nature operates. Limits exist not as arbitrary rules, but as consequences of specific physical processes. Change the process and you change the limit. The universe doesn't forbid massive black holes. It just makes them difficult to build under current conditions. The black holes we observe today, TON 618, Phoenix A, the ultramassive giants in distant galaxy cores, represent what's achievable in the universe's first 14 billion years. They've grown as large as accretion physics permits within the time available. They're not the maximum possible size. They're the maximum achievable size given current cosmic conditions. And that's a crucial distinction. Because conditions change. The early universe was different from today. Gas was denser, pristine, metal-free. Black holes might have grown faster through mechanisms we don't see operating now. The future universe will be different still. When galaxy superclusters collapse over trillions of years, mergers could build objects that dwarf anything we observe today. Those far future monsters, stupendously large black holes potentially reaching 100 trillion solar masses, represent the ultimate endpoint of structure formation. They're what happens when gravity has infinite time and mergers face no physical constraints. They might never actually form if dark energy keeps the universe expanding forever. But the mathematics allows them. General relativity doesn't say no. What we're witnessing now is just one chapter in a much longer story. The black holes currently pushing against growth limits are the first generation. Products of the universe's early energetic phase when gas was abundant and accretion could proceed efficiently. Future generations might grow larger through patient gravitational dynamics rather than feverish feeding. The measurements remain uncertain. TON 618 might weigh 40 billion solar masses, or 66 billion depending on technique. Phoenix A's mass estimates span a factor of 5. These uncertainties frustrate precise conclusions, but don't undermine the broader picture. The largest black holes cluster around a consistent range. They're approaching theoretical limits. The convergence between prediction and observation suggests we understand the fundamental physics, even if individual measurements carry error bars. Each new telescope pushes our view deeper. The James Webb Space Telescope reveals black holes that shouldn't exist yet, too massive too early. These observations challenge our models and force revisions. Maybe super-Eddington accretion was common in the early universe. Maybe direct collapse black holes seeded massive growth. Maybe primordial black holes gave some objects a head start. The answers will emerge from continued observation, from better measurements, from theoretical advances that connect accretion physics to cosmology, from gravitational wave detectors that catch supermassive black hole mergers and weigh them directly. The conversation between theory and observation continues because the universe keeps surprising us. What won't change is the basic framework. Black holes grow through accretion and mergers. Accretion faces limits imposed by disk physics and radiation pressure. Mergers face limits imposed by cosmic structure formation and gravitational dynamics. Both processes can build enormous objects, but neither can proceed unchecked forever. The maximum size of a black hole isn't written into the fundamental constants of nature. It's not like the speed of light or Planck's constant, a number you could measure in a laboratory. Instead, it emerges from the interplay of multiple physical processes operating across cosmic scales. It's contingent, contextual, and potentially changeable as the universe evolves. That makes it more interesting, not less, because it means understanding black hole limits requires understanding galaxy formation, dark matter distribution, cosmic expansion, accretion disk physics, gravitational wave emission, and quantum effects near event horizons. It's a problem that connects nearly every area of astrophysics. The black holes we observe today are messengers from cosmic history. Their masses encode information about when they formed, how they grew, what environments they inhabited. The largest ones tell stories of exceptional circumstances, gas-rich mergers, sustained feeding episodes, fortuitous orbital configurations that allowed continuous growth over billions of years. They're rare not because the universe can't produce them, but because the conditions for their formation are uncommon. Most black holes grow to more modest sizes. Most galaxies experience disruptions that interrupt feeding. Most accretion disks become unstable before building truly ultramassive objects. The champions we've found, the 40, 50, 60 billion solar mass behemoths, represent the lucky few, objects that avoided disruption long enough to approach the limits of what accretion allows. They're not the endpoint of black hole evolution. They're the endpoint of one particular evolutionary pathway. Other pathways might exist, ones we haven't observed or don't yet understand. The universe is large and old enough to have explored possibilities we haven't imagined. Every deep field survey finds surprises. Every gravitational wave detection teaches us something new. Every theoretical advance opens unexplored territory. The question, how large can a black hole get, doesn't have a single answer. It has multiple answers depending on context. Today, through accretion, around 50 billion solar masses. With perfect conditions and maximal spin, maybe 270 billion. Through mergers in the far future, potentially 100 trillion solar masses or more. The answer changes based on mechanism, environment, and cosmic epoch. What remains consistent is that black holes face boundaries. Not metaphysical limits, but physical ones emerging from how space-time responds to extreme mass concentration. The universe allows black holes to grow extraordinarily large, but not infinitely large. Not all at once. Not through any single mechanism operating without constraint. This is physics operating at its most fundamental level. Gravity warping space-time, matter responding to curvature, radiation pushing against gravitational infall, angular momentum resisting direct collapse. These aren't complications obscuring simple truths. They are the simple truths, playing out across scales that challenge human comprehension. The largest black holes in the universe represent gravity's ultimate victory over all other forces. They're regions where space-time curvature becomes so extreme that nothing escapes, where tidal forces could shred planets, where time itself dilates dramatically, where classical physics breaks down and quantum effects become relevant. Yet even these monsters face limits. The universe that created them also constrains them. Through accretion disk instabilities, through radiation pressure, through the finite age of the cosmos, through the distribution of matter available for growth. Understanding these limits isn't just academic curiosity. It connects to fundamental questions about cosmic structure, about how galaxies form and evolve, about the relationship between black holes and their hosts, about the ultimate fate of matter in an expanding universe. The M-sigma relation, that tight correlation between black hole mass and galaxy properties, exists because black holes and galaxies co-evolve. They grow together through processes that couple their masses. The black hole's maximum size constrains the galaxy's maximum size. Or perhaps the galaxy's properties constrain the black hole's growth. The causality flows both directions through feedback mechanisms we're still mapping. What's become clear through decades of observation is that the universe has produced black holes near the limits of what current physics permits. We're not missing obvious examples of larger objects. We're not failing to detect 500 billion solar mass monsters lurking in nearby galaxies. The largest objects we find cluster around predicted limits. That convergence between theory and observation validates our understanding. The physics we apply to stellar mass black holes scales up to supermassive ones. The mathematics that describe accretion disks work across 10 orders of magnitude in mass. General relativity holds from solar masses to billions of solar masses without requiring corrections. This doesn't mean our understanding is complete. The early universe black holes that formed too fast remain puzzling. The exact formation mechanisms for supermassive black hole seeds remain debated. The role of dark matter in black hole growth remains speculative. Plenty of mysteries persist, but the broad framework is solid. Black holes grow through accretion limited by radiation pressure and disk physics. They grow through mergers limited by gravitational dynamics and orbital decay timescales. These mechanisms can build objects of tens to hundreds of billions of solar masses in the time the universe has existed. Larger objects require either special circumstances we haven't observed or timescales extending far into the future. The story of black hole maximum masses is really the story of cosmic evolution itself, of how structure forms from initial quantum fluctuations, of how gravity battles against expansion, of how feedback processes regulate growth, of how the universe transforms from smooth near uniformity to the rich hierarchy of structures we observe today. Black holes serve as gravitational anchors in this story. They mark the deepest potential wells. They concentrate matter that would otherwise disperse. They regulate star formation through their energetic feedback. They record cosmic history through their masses and spins and merger rates. The largest among them, the ultramassive giants pushing against physical limits, represent the universe operating at extremes. They're test cases for physics under conditions we can barely reproduce in theory, let alone in laboratories. They're natural experiments in how space-time responds to concentrated mass. Each measurement refines our understanding. Each theoretical advance clarifies predictions. Each comparison between observation and calculation either confirms our models or forces revision. The scientific process continues because the universe keeps providing data. What we've learned is that nature doesn't do infinite. Even black holes, those cosmic vacuum cleaners that seem to devour everything, face boundaries. Not because fundamental laws forbid larger masses, but because practical mechanisms limit growth under realistic conditions. The 50 billion solar mass threshold for accretion-based growth, the 270 billion solar mass ceiling for maximally spinning black holes, the 100 trillion solar mass giants that might form through mergers in the far future. These numbers aren't arbitrary. They emerge from physics applied consistently across cosmic scales. And that's perhaps the most beautiful aspect of this entire investigation. We can sit on a small planet orbiting an ordinary star in an unremarkable galaxy and calculate the maximum size of the most extreme objects in the universe. We can predict what happens near event horizons billions of light years away. We can forecast the formation of objects that won't exist for trillions of years. The mathematics works. The physics scales. The predictions match observations within measurement uncertainties. That's not guaranteed. The universe could have been fundamentally unpredictable or governed by different rules at different scales. But it's not. The same physical laws that describe falling apples describe colliding black holes. So when we ask, how large can a black hole get? We're really asking about the limits of cosmic structure formation, about how matter collects under gravity, about how energy flows through accretion processes, about how the universe evolves from simple beginnings toward complex futures. The answer isn't a single number. It's a framework for understanding how different physical processes impose different constraints. It's recognition that the universe operates through mechanisms that allow extreme outcomes while preventing infinite ones. It's appreciation that even the most massive objects face boundaries emerging naturally from physical law. The black holes we observe today approach those boundaries. Future observations will refine the numbers. Theoretical advances will sharpen predictions. But the basic picture seems solid. Black holes can grow to tens of billions of solar masses through accretion, potentially hundreds of billions through mergers, perhaps trillions in the distant future if cosmic conditions permit. That's where the universe has drawn its line, not through arbitrary decree, but through the logical consequences of gravity, thermodynamics, and space-time geometry. The monsters exist. They're real, they're enormous, but they're not unlimited. And in that limitation lies profound beauty, because it means the universe makes sense. Extreme conditions produce extreme objects, but even extremes have boundaries. Physics applies everywhere, from the quantum scale to the cosmic. The same principles that govern everyday life govern the most exotic objects imaginable. That's the real answer to our question. Black holes can grow as large as physics permits, and physics, applied consistently across cosmic scales, sets limits around 50 to 270 billion solar masses for objects forming today. Future mergers might push higher. Far future collapse might produce stupendously large objects. But even those face constraints from gravitational dynamics and cosmic expansion. The universe doesn't do infinity. It does extremely large, unimaginably massive, but bounded by physical law. That's not a limitation. It's a feature. It's what makes the cosmos comprehensible despite its vastness and complexity. The largest black holes tell us where those boundaries lie. They're cosmic markers showing how far structure formation can proceed before physics says stop. They're monuments to gravity's power and its limits. They're reminders that even in a universe billions of light years across and billions of years old, nothing grows without constraint. That's the final lesson from our journey through black hole maximum masses. The universe is vast, but not infinite. Ancient, but not eternal. Extreme, but not unlimited. And the black holes within it, for all their gravitational dominance, ultimately respect the same physical laws that govern everything else. They're large. Incredibly, almost incomprehensibly large. But they're not infinitely large. They can't be. Physics won't allow it.